everyone, and welcome to another live stream study session for IFT 372. We're going to give it a couple minutes here just for everybody to show up and get prepared. I know we have a good deal of stuff to potentially go over. Again, for those of you who haven't attended before, I generally don't put together a schedule for these. I don't have a set of talking points I want to go over. It's mostly to answer questions you guys have. So I think the two main things are obviously going to be the midterm and the homework. But anything other than that is also up for grabs too, but those are the two I'm mostly prepared to talk about. But like I said, I don't have a plan for these, so we'll just post your questions as we go and we will get to them. Again, we're scheduled for an hour here, so hopefully we'll be able to address a good number of your questions. And then if I don't have time to go over anybody's particular questions, you can either email me or attend the study session on Sunday morning, which will be from 10 to 11. But email is fine too. I can get back to you within a day on email if you have something that's easy to just kind of talk through. But there is also Sunday as well for any last minute questions. And again, I think from what I was seeing, the midterm exam is available starting tomorrow, I think, for you to take that. So if you wanted to get ahead of that, obviously you can ask some questions today or you can wait. I'm not sure what the last day is. I'd imagine Sunday. But so again, we'll just wait a few more minutes just to make sure the people who want to attend can attend. Okay, so Al's just saying that the last day for the midterm is the 13th. Is there a session this Sunday? Yes, there is. There'll be one on Sunday morning, 10 to 11. Okay, so that's Tuesday's the last day you can do the midterm. That's nice. So we have a little bit more time on that. I would definitely, speaking of the midterm, just now that it's brought up, if you had been considering not doing a midterm practice, I would not advise that. It's definitely useful, and doing it will give you a pretty good idea of what's going to be on the final. Also, looking over the review sheet is a good idea, but I think actually doing the practice problems and commenting in the discussion thread that's already up will be very helpful. People who do that, it's very similar to what you'll be seeing on the actual exam. So going through it and making sure you can find any problems you have with the material or just being able to do the problems will give you a very good start for the midterm proper. We'll give it 2 more minutes till 5 after, and we'll see where we're at. it looks like, well, I've given enough time for people to show up late from the beginning, so we'll just keep going. It looks like there's actually a couple of people watching that just haven't left a comment, but either way, we'll get started now, and then anybody who has comments or questions can either arrive late or just get going from here. So if you have a question that you want us to start out with, please post it and we can get going. Okay, Al asks if we can go over question 5 in the practice midterm. Sure we can. So let's see, question 5. Okay, so question 5, let me get rid of this. Alright, question 5 tells us that we have a baseband signal with frequency components from 5 kilohertz to 15 kilohertz, and we need to A, determine sampling rate, and then B, the maximum interval between samples. Okay. So this question is basically focusing on the Nyquist sampling theorem, and that sampling theorem basically states that if we have a signal, I'll draw a very rough one out here. So if we have just a basic signal, we need to figure out, it's given a frequency. Every signal has a certain frequency to it. So here you can see if I draw time periods here, we basically just have a cycle every half second, basically, if we assume those lines are at a cycle, because we have 0, 1, 0, 1, 0, 1. And so what Nyquist is saying is that we need to figure out the rate that we need to sample this signal at. And in order to do that, if we have the frequency here of 1, so let me draw one more there on the end. If that's our frequency, and so it happens once here, once here, once here, we need to then figure out how many times we need to sample the signal, I guess, in order to get all the data recovered. And so here, if we have a 0 here, and a 1 here, and again, this is just a basic binary signal, if our frequency encompasses the whole 0 and 1, we would need to sample it twice in the frequency in order to get all the information, because we need to sample it here, anywhere on this side to get a 0, or anywhere on this side to get the 1. And so what Nyquist sampling theorem basically says is that in order to recover all the information from a signal, you need to sample at twice the highest frequency contained in the signal. And so if we look at our problem again, we see that our baseband signal has frequency components from 5 kilohertz to 15 kilohertz. So that means our signal varies anywhere between a frequency of 5 kilohertz and a frequency of 15 kilohertz. So all we care about for sampling purposes is our 15 kilohertz, because we need to sample fast enough to be able to get all the information contained when the signal is going at 15 kilohertz. And so for this problem, our sampling rate is twice our frequency max, and given the information we have, that's 15 kilohertz. And so our sample rate is 30 kilohertz. And so that tells us that we need to take a sample, we need to sample our signal every 30 kilohertz, or at a rate of 30 kilohertz. Because we need to be able to get all the information in the signal, anywhere from 5 kilohertz, which is sufficient. 30 kilohertz covers 5 kilohertz because it's at least 10. And then we need to catch our highest frequency, and 30 kilohertz does that. So again, we could sample faster than this, but this is the minimum rate that we need to sample at. The minimum rate that you need to sample at to recover all the information from a signal is twice the highest frequency. So that's answering part A there. We've determined the minimum sampling rate. And then part B is asking for the maximum time interval between successive samples. So if we know that we need to sample at a rate of 30 kilohertz, we can basically remember that just basically we have a rate which equals, let me think about how I want to explain this. So if we're sampling 30 samples, or 30,000 cycles per second, then what we really want to solve for is the amount of time each individual sample takes. And so that's just the inverse of what we're already looking at, right? Because the sample rate means we're doing 30,000 samples per second. That's what our sample rate is saying here. We have 30,000 cycles, 30,000 samples per second. And so if we invert that number, so instead of that, if we do, so we're doing, in 1 second, we need to do 30,000 samples. That'll tell us how much time we have per a sample. And that's what we're looking at. We're trying to find the maximum time interval between successive samples. And so if we crunch the numbers here, we have 1 divided by 30,000. And then let me just look here really quick. Come on. And Ashley just posted in chat saying, yeah, that's, so what we're looking at exactly for Nyquist sampling rate is 2 times 15 is 30. And so here, sorry, just having a little bit of slowdown. So that ends up giving us, here we go, 0.000033 seconds. And that's what we're looking at for the time between the samples. Because remember, and this is what always tripped me up when I was thinking about this problem before, is that a sample is, for all intents and purposes, instantaneous. So it doesn't take any time to do a sample. It's like taking a snapshot. It's instant for the sake of the problem. And so if our snapshots or our samples take no time, we can take a snapshot and then we can wait up to 33 microseconds or 0.000033 seconds before we take the next one and still be able to take 30,000 samples per second. And so that's what this question is asking, is the maximum amount of time you can wait between samples to meet your minimum sampling rate. And again, that's what we just did. And we had our sample rate. We had 30,000 kilohertz, 30 kilohertz, 30,000 hertz, or 30,000 samples per second. And so if we're doing 30,000 samples per second, like here, in order to find the amount of time it takes per single sample, we just invert that. So we know in 1 second we're doing 30,000 samples. And so that means if we divide 1 by 30,000, we find that there's 0.000033 seconds is the amount of time we can wait between our individual samples. Or you can basically say that in a second, if we divide it by 30,000 chunks, each chunk is 0.00033 seconds long. So the sample could take up to this time, or we could wait this long between samples if the samples are instantaneous. So again, we're starting for part A, you're just looking at the Nyquist sampling theorem, which states that you have 2 times the highest frequency is required to recover all the data back from the signal. And then for part B, you're just taking your sample rate that you just calculated and figuring out the amount of time it takes per individual sample. Yeah, the core formula that you'll see here if you want to review this will be the Nyquist sampling theorem. And then this math here is just an application of understanding, okay, I'm taking this many samples per second, how many samples fit in a second, or how long does a individual sample take? And again, that was question 5 from the practice midterm. So again, I'll just give it a second to make sure everybody's on task. If you're not, or if there's something that confuses you, please leave a message in the chat, or we can move on to the next problem as necessary, or as you choose. Okay, Stephen asking about question number 5 on the homework. Let me pull up and make sure I get which one you're talking about. So sorry, which question 5 was that? Was that... Let's see. Okay, thank you. Thank you for clarifying which problem you're talking about. Okay, so basically what you're looking at for this problem is that when you're saying that it goes up at the same constant rate when you double the distance, that's technically true, but it's not hugely helpful for the sake of this problem, right? Because we're not going at exactly double the distance, we're going at some weird, not quite double or a little bit more than double. And so there is a particular distance formula that you can use when you don't have the easy double the distance. Because typically you're absolutely right. When you double the distance, you have a loss of 6 dB. So here, I might as well start writing this down. So that's absolutely true. But again, that's only really useful when you actually have exact double distance. And so typically, by the rule of thumb, you can just say 2 times the distance equals minus 6 dB of loss. Just generally, rule of thumb, you can say that. However, when you're dealing with numbers that aren't exactly double, you have to use a little formula And the easiest way I think to use it is you have delta P, or change in power, equals 20 log, and then you have distance 1 divided by distance 2. And again, this is a decimal formula, and you can tell because we're doing division in here and then doing a conversion here. And so, for example, for this particular problem, we're trying to find, so we're given the received power at 1 kilometer is 1 dBm. So power at 1 kilometer equals 1 dBm. And so if we're trying to now find the power at 2 kilometers, that's a double. So we can do it in one of two ways. We can say, okay, it doubled, so we lose 6 dB, but I'll also show you how this formula works for it. So we have delta P equals 20 log 1 divided by 2. And then if we do the math on that, just got to clear out my calculator. That gives us a delta P, or difference in power, of negative 6.02, so 6 basically dB. And so either way the formula works for that one. So you can either just rule of thumb and say, okay, we doubled the distance from 1 to 2, equals, and so the power, we have to lose 6 dB of power, so we end up with negative 5 dB m of power at 2 kilometers. And then we can just repeat using that formula for our next distances. So our next distance would be 5 kilometers. So then how would we use, again, since that's not an exact double, we can't just use our doubling rule of thumb. So how would we apply this formula? This formula here, 20 log d1 d2 for our 5 kilometer distance for part B. If somebody wants to type out the formula we'd use for that one, we'll verify, and then since it's just math at that point, I'll leave you to figure out the rest and we can check answers. This even says 20 log 1 divided by 5, and yeah, that's true. That's correct. The important thing to remember is that you're not looking at the difference between each consecutive step, right? And that can be tricky. So Steven's done one. No, Steven, I think you're good. So let me see, Ashley, negative 5 dBm minus. Okay, so Ashley made the mistake that I was actually just talking about. You're not looking at the consecutive steps. So our D1 is going to be the distance that we know the received power from. And so we basically have to treat everything as fresh. And so we have to say when we're looking at the distance from 1 to 5, the only numbers we care about are the power we received at 1 and the power we're going to receive at 5, not what happened at 2. And so our D1 is going to be the original starting point, or the distance that we know the power at. So in this case, 1. And our D2 is going to be the distance that we don't know the power at. And so you don't have to worry about the 2 kilometer number for the 5 kilometer number at all, because you're looking at the power loss between the first and station X, whatever you care about, and you don't care what happens in the middle or any station in between. And so if we plug in those numbers, 20 log 1 divided by 5, it ends up giving us a delta power, or a change in power, of negative 13.98 dB, or basically delta P equals negative 14. and then we can apply that power change to find the received power at 5 kilometers. And then we can repeat for 20. And that's basically the rule of thumb formula you're going to be using, unless you can really just shortcut it and say, okay, hey, it's twice the distance, great. But for anything more than just a simple double of the distance, I would suggest using this formula. Alright, so again, we'll wait a second to make sure everybody's on the same page and everybody's caught up, but then we can go ahead and move on. We've had Stephen and Al propose a question, so I don't know if Ashley, if you have something you want to look at. Since we have so few people, we can just take turns, if that works. And this again, since Ashley, I haven't seen you in one of these before, or you weren't in the last one at least, I don't think. These videos are all available on my channel, recorded after the fact. So if you want to go back and watch over when we're done, they are available. And that link's available in the discussion board, hallway conversations. Okay, so Stephen has this one. Yeah, this one can be a tricky one with the power density. And so Stephen's asking, what is the power density in watts 30 kilometers away from a directive antenna that has a transmitted power of 38 dBm and a directive antenna gain of 24 dB? Okay, so we have let me see. The core thing we're looking at for this problem is we need our power density formula, or PR density formula. And does anybody have that formula on hand? I do. I just want to see if everybody else is on the same page. Yes, and so Al's provided the power density formula, which is exactly what I was looking for. So our power density formula equals power transmitted. I think we all get that. So power times gain divided by 4 pi times R squared. And so again, looking at this, we know it's decimal formula because we have 4 pi times r squared. This is we have decimal numbers in here. And so that means our p and our g have to both be in decimal, not decibel, in order to solve this. And so we know that our power transmitted is, let me just make sure we're all on the same page here. Okay, so we know that our transmitted power is 38, or I guess I'll just do P equals 38 dBm. And we know that from the problem because it says that the directive antenna has a transmitted power of 38 dBm. So that means when immediately after it leaves the antenna, or we're transmitting at a power of 38, so we're not assuming any loss has happened at that point. And then we know our directive antenna gain is 24 dB, and again, that's given from the problem. And then 4 pi is going to be a constant because we know the value of 4, we know the value of pi, those don't change, they're not variables. Then r squared is what we're looking at for our density. And so if we're 30 kilometers away from a directive antenna, that's basically the tricky part, is that we have to know that for this purpose, the radius is going to be 30,000 meters. Because if the antenna is in the middle and we travel 30 kilometers away, that's the radius of the sphere from the antenna. Because remember, we have a sphere centered on the antenna. The radius is going to be, if we walk away from the antenna in a straight line, that's just the radius, because it's also broadcasting on the other half, or on the other side of the antenna, the same distance. And again, we went from 30 kilometers to meters. I always try to work in the smallest unit, or the base unit, I guess you could say. So again, because this is a decimal equation, we can't use decibel values, so we need to do our conversions here. So if we remember how to convert our decibel units, I'll let somebody do that for me. So if we just remember how to convert our decibels, I'll do it as well, but I'll let somebody post it out just to double check. Because there is also one tricky thing here, which we'll address in a second. And I'll post the conversion there. So if we're converting from decibel to decimal, we do 10 to the decibel divided by 10, and that gives us our decimal. So for example, here we have 6309.57, and then here we have 251.1886. Now, let's see if anybody caught the tricky thing. There's something we have to consider about our power value here. Can anybody see what? And there, Stephen basically got the drop on me and said, do we have to convert this to dBW? And yes. So the problem here is that we went from dBm to decimal, which means that this number is in milliwatts, which is not what we want, right? We want to work in the base unit. So we need to convert this number from milliwatts to regular watts. And that's the tricky thing to remember, is that dBm is milliwatt in decimal. And so we want to convert that back to our base unit, and Stephen gives us the conversion as well. In order to convert from milliwatts to watts, we divide the number by 1,000, so that gives us 6.309 watts, and that can round to 6.31, generally close enough. And so that can trip you up if you're not paying attention to your units there. And again, I find it easiest to always work in the base units. We could have kept in milliwatts, but we would have to make sure all our other units matched. So we wouldn't be able to use meters down here for the radius. We would have to use millimeters. And then we'd have to convert our answer back anyway. So because we want our final answer, the question asks the power density in watts. We want to just stay in our base unit of watts. It just makes more sense. Otherwise, we have to convert either during the problem or at the end, and I think it's easier to keep track of if you just stay in the base unit as soon as you can get there. So now that we've converted those numbers over, into their proper usable forms, we can just plug them into our formula. So again, we have our formula up there. So we have 6.31 times our gain of 251.1886 divided by 4 pi times 30,000 squared. And so if we do that math, that gives us a very small number indeed. And just going back over the chat, Al asked, couldn't you change from dBm to dBW, then change to decimal? And yeah, you could absolutely do that too if you wanted to do it. You're doing the same thing either way, right? Because dividing by 1,000 is the same thing as subtracting 30. So you're doing the exact change. That comes down to preference, whether or not you whichever you feel more comfortable doing. Both ways work just fine, and you get the same answer. And so plugging in these numbers gives us a very small number. And again, this is a case where you can either, if you're comfortable with the metric system, this answer kind of makes more sense to write out in the metric system. But if somebody wants to post the answer they got 2, I'll see how you format it, and then we can talk about how to format the answers. And this is a good calculator problem to make sure you know how to type numbers into the calculator. Make sure you get order of operations right. Steven says 5,500 nanometers. That is not what I got plugging it in. So you may have had a calculator mistake. Let me make sure I wrote all the numbers down correctly. Does anybody else have a number to compare against? Because I'd be curious to see if that was just a calculator mistake. Okay, I'll give another number which I did not get. So this is curiouser and curiouser. Anybody else have a number to compare against here? Because I'll write out the number I got and then we'll see. It's possible I made the calculator mistake. Here, let me write out the number I got. So when I put these numbers in, I got 1.4014. And some of you might be making adjustments that I did not for. I'm just going to write out the full number for the sake of times 10. So that's what my calculator has given me. Okay, so yeah, Ryan and Ashley got the same number I did. And so I'm not sure, Stephen, why your number would be so much higher. So it sounds like that might have been a calculation problem. So we can break it down by chunks. We can say, if we do the first half, so this will be a good test to see if where the calculator went wrong. So for the first parentheses, I got 1, 5, 85.0000066. Okay, so Steven figured out why his... Oh, he forgot the 4 pi. Okay, yep, that'll do it. And that explains why you were... Yes, okay. So I will not go over the math. And so this is what the number we've got, and this is in watts per square meter. Because remember, we're talking about a power density, and we squared our meters right here. So we did... This is square meters. So we know we're going to be over square meters, and then we also have our watts times a non-unit value. So we have watts over square meters. And again, this is down to preference, where you can either leave this answer as is, and that's fine, or if you don't want to have this ugly of an answer, having 10 to the negative 7, we can do metric, and like Steven was doing, we can convert to nano. So instead of saying just basic watts per square meter, we can instead write this as 140.14, and again, you can kind of not worry about the decimal places too much, 8 nanowatts per square meter. And so you can write it out. Again, that's if you're comfortable with the metric system and you know your conversions like that. And again, just nano is 10 to the negative 9th. So we moved our decimal place over 2 to the right to add 2 more to the negative 7 to get negative 9. And then we have nanowatts instead of basic watts. And it just makes the number a little bit cleaner. But you certainly don't have to do that. The two answers are equivalent. This is a case where if you wrote one on the test and it was looking for the other, it would be something where we'd review it and give you the credit for it either way. So whatever you're comfortable with. When in doubt, I would always write out the exact number just because it's one less place to make a mistake. But again, that's down to personal preference. Either of those answers are okay because they're both the same. But that's all we're looking for this problem. So again, just remembering the power density formula. And it kind of makes sense when you look at the formula because you have power times gain. So you basically have your total amount of power or signal strength. And then you're dividing it by 4 pi r squared, which is basically your area. And so it kind of makes sense what that formula is telling you. It's saying that per square meter, you get this much power. That's what we're looking for that problem. So if that makes sense and everybody's good, we can move on to the next problem. Alright, Al asks for number 6 from the practice midterm. Let me pull it up. Okay, so yes, number 6 is asking, a digital communication system is being designed with the goal of transmitting 32 kilobits per second. And I guess I will start. So we have a goal of 32 kilobits per second. Let me just make sure we are actually working on this problem. Oops. Okay. So So we have a goal of 32 kilobits per second over a channel with bandwidth equal to 8 kilohertz. And we need to A, determine the number of encoding levels, and then B, we need to find the minimum SNR required. Okay, so looking at this problem, we have a communication rate, right? We want to hit 32 kilobits per second. We have a bandwidth, and then we have a number of levels and an SNR. So can anyone think of a formula that would use communication speed or rate, bandwidth, and then number of levels? And then what about SNR? So we'll start with just part A. So I guess we'll say, can we think of a formula that uses these three variables? Number of encoding levels, bandwidth, and communication rate. So Ryan says Nyquist sampling theorem, which is true, that would use the bandwidth. But if we're trying to find the number of encoding levels, Stephen's correct in saying it's Shannon-Hartley. So normally we're used to solving for the goal. But in this case, we have to solve... No, Stephen, you're right. We have to solve the other way around. And so Stephen's posted out the two Shannon-Hartley formulas. So we have 2b log of m, and then 2b 1 log 1 plus SNR. Now careful, Stephen, with your numbers, because they're not both 2b. And so Stephen's correct, but he made a little mistake with the SNR formula. So this is a Shannon-Hartley problem. And again, those two Shannon-Hartley formulas that we're going to be using are 2b log 2 of m and b log 2 of 1 plus SNR. And so those are the two formulas that we use for Shannon-Hartley. And actually, let me write out the full formulas. And we're used to solving for C in these problems because we're typically given a bandwidth, encoding levels, and asked to find the channel capacity. But in this case, we're given C, we're given B, and then we need to find the other bit. And so looking at these problems, for part A, we're trying to find the encoding levels. So we need the first formula. So we have C equals 2b log 2 of m. And again, we use this formula because we're trying to find the number of encoding levels, which is m. And we have a bandwidth, and we have C. So we're solving for m. So if we plug in our numbers, we have 32,000. And again, I'm converting from kilobits per second to bits per second. Equals 2 times 8,000, doing the same conversion here, log 2 of m. And so we have to solve for m here. And so we'll do some algebra to get us started here. Let me make sure everybody's on the same page, okay? And so we can solve out some of the numbers. This is just algebra. We're just solving down our 2 times 8,000 because we're trying to isolate the m, right? Because we're trying to solve for m. So now we can divide out our big numbers that are easy to handle. And so now this is the typical tricky part that people get left with, is that we have 2 equals log 2 of m. And sometimes people forget how to do their logs when we hit this point. And so how do we handle this, given these numbers? How do we solve from this point? Because this is the point where a lot of people get stuck, is they don't know how to handle this log. And there's a couple ways to do it. Either your calculator handles it or it doesn't, which is the fun way of doing it. But and so Stevens basically got it. We raised 2 to the 2 because if we remember how logs work, say we have log base 2 of 4. Let's say we're dealing with this. This is our problem. And the answer to log base 2 of 4 is 2. And what this question is basically asking us is we have what number on this side do we have to raise 2 to in order to get 4? And actually this was a serendipitous example, but whatever. And so the answer on the other side of the equal sign is what we have to raise the log base to in order to get the number inside the parentheses. And so that's the important part that people tend to forget about because they're not used to dealing with the basic logs, or they're not used to solving for the inside number in the logs. So another example would be log 10 of 100, or let's do 1,000. Log base 10 of 1,000 is equal to 3 because we have to raise 10 to the third in order to get 1,000. So in this case, if we raise 2 to the 2, we solve m is equal to 4. So we would need 4 encoding levels given this scenario. And that's our answer. We would need 4 encoding levels to have this system work. Using a bandwidth of 8 kilohertz, we need 4 levels to get a speed of 32 kilobits per second. And we can double check the math by plugging the numbers back in. So if we have 2 times 8,000, oops, wrong log. Log base 2 of 4, we get our answer. So I just double checked it by plugging the numbers back into our formula. So if we solve for m, we can do 2b log 2 of 4. So 2 times 8,000 log 2 of 4, and that gives us a c of 32,000, and that's the number we want. So we know that that's the right answer. And now we basically have to do the same thing for part B, except we use the other Shannon-Hartley formula of log 2 1 plus SNR. So this is part A over here. Over here we have part B, which is C equals not 2, just regular B log 2 of 1 plus SNR. And again, our SNR in here is going to be decimal because we're adding 1 to it, which means it's a decimal equation. So we plug in our numbers, 32,000 equals 8,000 log 2 1 plus SNR. And we'll cancel out with algebra, cancel the numbers out. So we have 4 equals log 2 1 plus SNR. And then we're in the exact same situation we were on the other side. So if we apply the math here, exactly the same as we did in part A, what do we end up with? What's the next step of our equation here as we're solving? And so Stephen has 2 to the 4 equals 1 plus SNR. So again, remember that in order to find what's in the parentheses, we need to raise the base of the log by the other side of the equal sign. So we have 2 to the 4 equals 1 plus SNR. And we don't need the parentheses anymore because it's the only thing on that side of the equation. So that gives us 16 equals 1 plus SNR. And so that gives us an SNR, I guess I'll write it the other way around, of 15. And again, this is still decimal, right? And so we can leave it as such, or we can also get the decibel number. But this is not dB, and I nearly just wrote it out there, because normally we see SNR and dB, but that is not what we have here. We just have decimal 15. And so we could write that out as dB alternatively. And again, to do our dB conversion, we do 10 log. So 10 log of 15 gives us a decibel SNR of 11.76 dB. And again, the question, let me just double check. The question doesn't specify if they want a decibel or decimal SNR, so you can leave it as either or. I would probably leave it just in decimal, but I wanted to show you not to make the same mistake I just did, or almost did. You could leave it, I would leave it as decimal for this question since it doesn't specify, but be aware that you could write out either way. And Al says he always gets lost on finding the right formula to use, and yeah, it really is the best advice I can give for figuring out the formulas is looking at what the question gives you and just finding a formula that fits. Because there's only one formula that I can think of off the top of my head that uses kilobits per second, a bandwidth, and a number of encoding levels. And so the question will typically give you the clues that you need. But that can be complicated, especially with those questions that give you a big list of variables that they get at the beginning. Like, I think the activity had a problem like that, where the activity just says, spits out a whole list of variables at you. That can make it a lot harder. But for something like this, generally, I just try to look and see what I've got to work with, and then just do what I can with it, basically. And then again, that is a little bit of a weird application of Shannon-Hartley, or one that you're not necessarily used to, because we're used to solving for C, not M and SNR. So we are right about bumping up on time. Let's do one more. So if somebody has one more problem, let's take on one more problem. And then again, if we didn't get to all your questions, or you still have something that you're really stuck on, email me or check in on the Sunday session. But again, if you really need to have something answered, I would definitely email me or make a post in the discussion board, because that guarantees you'll get answered, as opposed to these study sessions where we might just not have enough time. All right, so let's just really quickly clarify. Ryan has a question. Ryan, post your question on path loss, and we'll take a look at it. And then I'll double check Ashley right now, just to make sure we're on the right step. So for number 2, it's asking for the received signal level of a system that has an EIRP of 64 dBW, path loss of 134, a receive antenna gain, and a receive transmission line loss. So let's see, RSL equals IRL plus gain minus transmission line loss. Yeah, Ashley, so it looks like you have it down there. Okay, so Ryan wants 16. I'll get to you, Ryan. Ashley, you're right. Yep, that's the formula you need, but then you also need to make sure you can find the IRL correctly. So that's absolutely the right formula. Just make sure you're getting IRL correct before you do the rest of it. So Ryan says 16. Let's take a look. Okay, yes. So I see what you're saying here, Ryan. Let me pull up the question here, Ryan. So Ryan, which did you have a formula in mind for 16? And again, 16 is given that a repeater is 25 kilometers from a transmitter sending data at a frequency of 1800 megahertz, what is the path loss between the transmitter and the repeater? Okay, so Ryan, can you post what formula you were thinking of using or planning on using? And then we'll double check what you're looking at. So again, we're looking at a couple specific numbers here. We have the distance, we have a frequency, and we are trying to find the path loss. So Ryan's got the formula 92.4 plus 20 log f plus 20 log d, where f is frequency and d is distance. And so your question is about the 92.4 in the front. Sorry, my notes computer is taking some time here, so give me 1 second and we will take a look. And yeah, so you've seen some other constants used in the lecture notes. Yeah, this one is a tricky one, like you said, to make sure you're using the right constant for the problem. That looks right to me, but let me verify. So yeah, so what you're looking at for that problem is, let me get rid of here. Oops, come on. So for this formula, you're absolutely right in that 92.4 plus 20, or let me write out the way you have it, 20 log f gigahertz plus 20 log d. So that's the formula you want to use if you've got frequency in gigahertz and a distance in kilometers. Al says we just need a giant sheet with all the formulas on it, and the class last semester definitely did that. I know there were a couple of students working on their own unofficial formula sheets, and yeah, it can be certainly useful, especially with an explanation of why you use the numbers when you do. And so the two main formulas that you're looking at here, I think, would be, you can use either this formula to do it, or you can have 20 log f, 20 log f in hertz plus 10. I'm actually probably not going to overcomplicate this too much. We'll stick with this formula. But yeah, this is the formula you want to use for path loss, given that you have a frequency in gigahertz and your distance in kilometers. And so that's why this formula works. And again, we can break down why that number is different. But as far as the other ones, if you want to email me, I'll take a look and explain the difference in more detail. But this formula is absolutely, you're using the right one for this problem. But I'd have to see some examples. I can't think of I know what you're talking about, and that there's different constant formulas, or there's other variations of this with different constants, but I would have to see them in front of me, and I don't have them in front of me right now to be able to explain the difference. But that would be a good one to email me about, and I can get a little bit more specific and maybe make a post about it, clarifying when you would use which when. And Al says he's going to start a post in the discussion boards. That's a good idea. Brian says he thinks the others are for non-free space environments. That's entirely possible. There are several loss formulas for several different environments. All right, we could probably squeeze in one more if somebody has one. But as Steven says, yes, there will be a session on Sunday. It is 10 to 11 a.m. Arizona time. And again, that'll be another hour. That one is pretty tight on the time, so I can't really overstretch time on that one. So 10 to 11 is pretty set in stone. So again, if you have a question that you think you really want to get answered either before Sunday or you want a good explanation, email me, because that guarantees I'll get to your question. But yes, there will be a discussion or a study session on Sunday where we will be going through this again. Those Sunday sessions tend to focus on the homework. So I would say if you're going into it looking for midterm practice, I think I'll put a priority on the homework on Sunday because it's due that evening. And we have a little bit more time on the midterm since you have until next Tuesday. I think somebody said the 13th. So I will say that there will probably be a homework focus on the session on Sunday. But again, email me with any specific questions for midterm practice or homework before then. Al gives a quick question. Noise figure is dB and noise factor is decimal, right? Yes, Al, you're right. Noise figure is dB, noise factor is decimal. NF is dB, F is decimal. Steven says he has a question on 26 on the practice midterm. Let me take a look. I think we have time to go over that. This will be the last one, but I do think we have time to go over it. Okay, yes. Okay, so yeah. So for 26, for all like the PCM questions, I need to do a little bit review on my own because we did not have to cover them in particular detail. So I'm a little rusty on it myself, but I can at least do the first part. So determining the voltage range result. What was your specific question, Steven? Did you just not know how to start it, or? Okay. Yeah, well, I'm kind of right there with you too, because it was a long time ago, and I don't think we covered this section in particular detail when I was in here. But from what I could see is when you're looking at, so we have our value or our number. So our PCM code is 1 0 0 1 0 0 0 0 0 0 0 1. So that's the PCM code that we're looking at. And again, the important thing to note with this is that it's sign magnitude, which means that this first bit here is just used to indicate the sign of the number, which means it doesn't actually represent the value that we're trying to transmit, right? Or it doesn't represent the value of the code. And so let me look here really quick. And so whenever you're dealing with sign magnitude numbers, that first digit is basically just indicating your sign. And as far as I remember, is that a 1 should indicate a negative number and a 0 is a positive number, but I need to double check with Dr. Helm on that because I was seeing some evidence to the contrary. But, one second, I'm just pulling out my notes. I'm going to do a little bit more reading up on this as well, and I'll probably make a discussion post about it. It might be worth, I am also going to review Dr. Helm's notes on, when was this? I think week 2. Let me see here. And so Stephen asks if you have to flip the bits. I don't think you have to flip the bits. So from my understanding is that if we ignore this first bit because it's just indicating sign and we just look at the magnitude, we have a binary number here. And so if we convert that binary number to a decimal number, which you can do, if you do it by hand, more power to you. Windows calculator has a binary mode that makes it easier. 1, 2, 3, 4, 5, 6, 7. I'm just Googling it, and that gives us $257 is what I get when I do that conversion. And again, it would be negative because the leading 1 indicates it is a negative number, and that's what the sign magnitude is telling you. And so when we have this number here, and then if we look at the problem again, it says that determine the voltage range result when the PCM code is converted into a decimal value. And so we have a resolution of 0.02 volts. And so I think the trick is just, now that we have this number, we just have to multiply it by our resolution. So times 0.02. And that gives us negative 0.14. And so I think the voltage range, or volts, I guess I should say, would be 14 to negative 5.12 volts, I think. Again, this is something that I need to research a little bit more. Okay, so actually, if that's what Dr. Helm said, that it's the opposite of what we learned, that was my main question to him. Because what I was looking at seemed to indicate it was the opposite, but I didn't have a good source for it. Okay, so thank you for clarifying that. That means that this is not negative. Because that's what I was going off of. I was going off the old information that we learned in that prior class. So we'll just switch everything over. And then this would be 0.16 instead. Do you remember where he said that, Ashley? Do you remember if it was in one of his video lectures? Because that's something I need to go look at. But anyway, I think that's what you're looking at for that sort of problem. I need to do more research, and I will make a discussion board post clarifying some of that as well. But it looked like some of the material was in week 2. I'll go take a look, but I think it was week 2 was where I was seeing some of the lecture notes on this. So, okay. Yeah, I'll go take a look, but I think that's what you're generally looking for this sort of problem, is that you have to find the decimal value of the PCM code and then multiply it by your resolution. But I will go double check and make sure I understand why exactly you have to do that, because I'm a little rusty on it myself. And then remember, it's a range. The only reason why we do 514 to 516. So 514 is what we get by doing 257 times 0.002 or 0.02. But then it's a range, and if we have a resolution of 0.02 volts, it would be anywhere between those two numbers, because basically we have an error of, or we have a resolution accuracy of 0.02, so it could be anywhere between 5.14 to 5.16, because the previous section would be 5.12 to 5.14. Or at least that's what I've got right now. I will do some more research and double check, make sure that's all correct, and I'll make a post about it if I find something that gives more of a thorough explanation on that. But yeah, again, that is not something that I remember having to do back when I was in the class, so I am not as up on it as I am with the rest of it. But I think that will just about do it for this study session. Again, I've said it a couple times, but email me if you have a specific problem that didn't get addressed. This lecture will be recorded and available probably later this evening, if not by tomorrow. And we will have one on Sunday, 10 to 11. It's pretty tight on that, so it is pretty strictly an hour. But I will see some of you then, and thank you for coming. And Al, making that formula sheet sounds like a good idea. So if you wanted to start that, I'm sure other people would appreciate it. Okay, that'll wrap it up for today. Thanks everyone for coming, and I will see you Sunday or next week.